on-demand measurements of greenhouse gas emissions using aerial robotic systems. Speaker is Dr. Javier González Rocha. He is a visiting faculty fellow in the Department of Aerospace here at IIT. His primary position is with University of California, San Diego, where he's applied math. Prior to that, he did his PhD in Michigan and postdoc. And he's interested in aerial robotic systems for atmospheric management. And visiting him and meeting. So I won't take any more time. So
All right, thank you. So my mic is on, so I can get started. So, it's a pleasure to be with you. I gave the first presentation in January. I don't know, I tried to some people were there for that presentation. Maybe a couple of you. So great. So I'm excited to be back here. Today's conversation is going to be a little bit different. So I will talk about sort of again touch a little bit on my work with aerial robotic systems and how I'm using it. And then the goal of this talk is to sort of kind of show you what I consider a big problem that we can help address with aerospace. My goal is to share some of the things that we're doing at UC Santa Cruz in collaboration with UC Riverside and other universities. And also sort of kind of opening the conversation for collaboration, right? What are the things that we can address in UC Santa Cruz? Working this space. Methane is a global challenge. It's not just a U.S. thing, but it's something that impacts. So let's get started. So I titled this presentation for on-demand measurements of greenhouse gas emissions using aerial robotic systems. And before I jump in, I sort of kind of want to give you a big scope of sort of my research. One of the things that I'm very interested in about how do we use aerial robotic systems to sense the atmosphere. And the thing that motivates that sort of this project are multiple things. So on the left, which is what most of this talk is going to be about, is environmental flow patterns, right? So how do we monitor them? What do I mean by monitoring them? How do we detect them in an quick and an effective way? How do we quantify them to understand how bad it is? And then how do we make decisions? Right? So on the left, I'm showing you a natural gas leak that actually happened in the Los Angeles, the Aliso Canyon. It's tons and tons and tons of natural gases being and you can see in the background, that's the city. So this has tremendous impact on the city, right? So we quickly want to assess the situation, and we want to be able to deploy assets to another thing is precision agriculture. So food security has become a big challenge, and as climate change becomes stronger and stronger and stronger, the agriculture sector is being impacted. So we have to be more precise about how we do this. Understanding what the atmosphere is critical. I'll give you the example of plant fertilizer and pesticide. As we want to increase the efficiency, we want to understand what the right conditions are. Why? Because if you have, for example, too strong of a wind, the fertilizer or the chemical that you're applying might blow away, and it doesn't get to the plant, it actually impacts it, right? And then the other one that is very relevant to everyone is weather forecast. I understand this working being able to understand the ocean atmosphere interactions is very critical. Right? Need more measurements of weather development. Now, just to further motivate this, how many of you, just by a raise of hand, have worked with a wind sensor? Yes, so when we think about wind sensors, there's two types of wind sensors. So there are in situ sensors and a remote sensor, right? So what is the difference? So on the left, you have an in situ sensor. It's local, right? So it's giving you a local measurement. What are the benefits of these sensing capabilities? Is that most in situ technologies give you a high to poor resolution measurement, right? Meaning I can get 100% of it. What is one of the drawbacks? One of the drawbacks is that you only get a single point measurement at a location. You want to understand how a wind field is changing. we need many of these, right? And although they are lower cost than most of included in the price, when you begin to have a network of these, and to the right, I have sort of remote sensing. There are obviously more remote sensing solutions, but these are some main ones. So the first one is the solar. So the solar is just essentially an array of speakers that chirps that it keeps going into the atmosphere, and then it waits for the back scatter. And based on the return signal, it translates direction. The value of the sensor is that it can retrieve a column. But it can tell you what the wind velocity is at different, right? So it increases our spatial response. The LiDAR does the same thing. It's working on the same principle. The only thing is that instead of emitting an acoustic signal, it's emitting a light signal. But it's more expensive. Now, what is the problem with this technology beyond it's more expensive? It's also the poor resolution. Right? So there's no perfect solution. That sort of kind of has been driven sort of the question of, what is the role of air robotic systems? Can they help close the gap in observations that we have resulting from the limitations of technologies, right? I'm very much interested in this because these technologies are very mobile and easy to operate. Now, solely speaking about the wind, there's almost two approaches to sensing the wind. So the first approach is treat the aircraft as a sensor. In this case, so the point here is the sensor at the top, the sonic anemometer, right? So that is your wind sensor. And so we're essentially just scanning aircraft carry. What's the problem with this, or what are some of the drawbacks? Some of the drawbacks is that one, you have to carry an additional cable, right? So that limits the flight time of the aircraft. You also have to supply it with power. And if you're drawing power from the actual aircraft, you're also limiting the impact, of the flight. Or if you carry a power source, then you also increase it. The other thing is you're corrupting the actual wind flow that you want to measure. So you have to take into account what is the error that's introduced by the propellers. That requires a lot of. Finally, the other thing is this thing is moving and it's in motion. Right? You have to think about how do we correct for the motion. So there's been a newer sort of methodology, and they're not always competing, and sometimes they're complementing, but the idea behind this other methodology is that we actually use the aircraft itself as the wind sensor. But if you look at the motion of the aircraft, look how it's responding, it's applying control velocity. And very first experiments that were done in this space sort of just all characterizing the kinematic relationship between a constant wind speed and the tilt of the aircraft. And a lot of these experiments were done in a wind tunnel or in low wind conditions. Now, what's the problem with this? The problem with this is that these models assume that the wind doesn't change. It's not realistic. So a lot of our research has focused on thinking about how do we actually use dynamic models for wind velocity, right, to capture the wind. I don't want to go into long details, but just tell you the story. This is part of my overall research is essentially explore how different models work for velocity. Using kinematic particle, dynamic particle model. So, the short summary is each one of these models increases. They're capturing something else that the previous model didn't capture, right? So the kinematic model we don't consider that. The dynamic model we're not considering forces. And the robotic model now we're finally and a lot of this work was done in the using linearized models about certain equilibrium flight conditions. Validate how good of a model they are. And then just to show you, and see if this will play. This is just once we develop this model, we essentially do experiments and we test them to see how good of an estimate we can get. And we do this comparing it against the weather. I just wanted to go back and show you. Okay. So I hope people can still see that. Okay. So just to show you some of the black is the ground truth, and the different signals that you see there, the green, the red, and the blue, those are the different. What's the story? Overall, those models do pretty well capturing the trend, but in reality, including additional fidelity in your model is actually helpful. So that's great. That was sort of kind of my PhD study in developing these algorithms for estimating wind. Yeah, so it's from a sonic anemometer. So the sonic anemometer is installed here at the top of the sonic anemometer.
That gives you a wind velocity only at that height?
Yeah, only at that height. Yeah, it's only given as a point measurement. And there's some things to consider, right? So the wind is changing with space and time, right? So it is a challenge, the fact that we can't put the same place, but we're trying to get as close as we can do, without one corrupting the other. This is not long. So then very quickly, we extended those frameworks, so we improved vertical profiles. So not only can we measure the wind while holding station, but we can actually move. Which is very important for a lot of applications. So great. So that was sort of kind of the beginning of my research, and more recently during my postdoc, I started thinking about, okay, this is great. There's a lot of relevance in understanding the waveform. What else can we use this? And upon my arrival to UC Riverside, I started learning about methane. I knew nothing about methane on there. So it's been an interesting journey in the sense I've learned a lot. How many of you, just by a raise of hand, have heard about methane before? Very high. So a couple of you. So methane, so just to put it into perspective, so this is on the left, so this is some data from NOAA, right? And so these trends are essentially showing you carbon dioxide, methane, nitrous oxide. This is sort of how they're increasing in the atmosphere. So this is the global measurement. So there are observations in different places that are looking at it and all the global output. And so when you look at this, you see what are the trends are, right? And what do you see? So they're all increasing. Right? Now, why is this critical? Is because greenhouse gases are basically gases that stop energy, right? They stop heat in the atmosphere. So this is what's driving climate change, right? And to put it in perspective, so methane has a global warming potential of 25 times greater than CO2. Right? So whether there's already a lot of focus on CO2, but sort of methane is very important because of this number, 25. And when you look at the 100-year horizon, that's closer to about 30. Right? Now, the other thing is that in terms of causing climate change, so methane, as I mentioned, is the second most powerful after CO2. The good news is that the life cycle of methane is about 12 years. So if you want to see change, if you want to see a sort of kind of deceleration of climate change, focusing on methane is where we can get the most money for our bank. And just to give you an idea here, if you look at the graph to the right, so there are this is what's called the global methane budget, right? So it's looking at where are the sources, where is methane coming from, then what are the seeds? What are the things that are absorbing? So we see agriculture, waste, so this is landfills, wetlands, fossil fuel production and use, and other natural emissions, biomass burning, they all contribute. Now, what's the problem when we look at the sinks, right? So sinks, a lot of them are borders to these sinks, but when when you look at the two values, what's the big problem? Is there anything that sort of stands out at you? Are they in balance? When you look at, so let's see, total emissions, 595 million metric tons a year, and total sinks about 570 metric tons a year, right? So there is a disbalance. So this means that the methane that's in the atmosphere, I think, probably see that. Now, why is this relevant to India? So these are some just data that I gathered from the Indian Ministry of Environment, Forest and Climate Change. So it's estimated that about 409 million tons, this is CO2 equivalent, are emitted in India every year. And this is, of course, a little bit outdated from 2016, but I wasn't able to find anything more updated yet. But it gives you an idea of the breakdown. So now, you have about 74% of the emissions. Waste is 14%. Then energy is about 11%. There's a missing 1%, and that comes from manufacturing and other activities. Right? So at least this gives us paints a picture of where we could take action to try and mitigate, right? So it seems that agriculture waste can be some focus areas. And so here the picture that I'm showing you is actually a satellite picture that was taken. This is in the city of Dubai, and so this is over the land. Satellite, and it's estimating what the emissions are. It's estimating that it's about 6.2 thousand kilograms per hour. That's a lot of methane. But again, as it says here, and I invite you to explore this with the website is cautioning low number of samples, right? So we don't have enough data. There's still a lot of uncertainty, right? And that's the problem is when we think about, okay, well, how do we mitigate methane? We have to think about sensible regulation. And how do we come up with sensible regulation? We need accurate quantification of what we actually want. So now we're talking about sort of some of the work that I've been doing in the U.S. and California specifically. And so when I started in this space, when I started looking at methane production from dairy farms. And in the state of California, about 50% quite a bit. So if you look at the graph on the right, all that you see in red, the red dot, those are all dairy farms. We have a lot of cows. And the emission estimates are highly uncertain. And so there's a tremendous need for high fidelity observations of winds, turbulence, and our composition with the planetary environment. So what I've been thinking about is how do we complement conventional observations? And I guess here I have included ground, because that's also a big part of it. Satellite, aircraft, and we're the drones to understand the atmosphere, especially because the atmosphere is highly. So we started thinking about how we can combine these methods to improve wind velocity with low cost solutions. And so this was work that was developed in partnership with Monsoon and Dr. Collins from UC Riverside. So they designed an airport, and so the airport here, I'll use my pointer, the pointer should still work. So it's just this coil. There's this long piece of tubing, we're talking about 50 meters of tubing that's coiled up, and we're turning it 5 meters below. Now, this coil of tubing is connected to an air pump. And inside of the air pump, there's an orifice. The orifice regulates the flow that's going through the tube. And so what we're doing is we're doing these vertical flights. So starting at the ground, we go up to 120 meters. And we come down along the airport. So we go up to 120 meters. There's some air in the airport. Then we dig into the sand. And then by that time, the airport is open. What we're doing is just dropping the column. Right? And this system gets its name from sort of this idea of an ice storm, where you can capture ice samples. And just to kind of give you an idea, this is what the actual air core looks like. So it's just a coil connected to the pump. So we fly, we collect the sample, and then we come down and we connect. So this is a cavity ring down. Basically, a sensor that shoots a laser through the air you collected. It based on the source or the rate of source. So just to sort of kind of give you an idea of the facility where we're working, so that's the drone on the left panel, and then this is an aerial picture, or a satellite picture, I should say, of where the drone operation took place relative to the dairy farm. Dairy farm, just for context, measurements here, so 800 meters wide, 945 meters long, almost a kilometer. This is pretty. It's a big. Right, and this is just a closer look. And one of the things that I want to point out, so there's different things that are going on in this facility. So here you have the different corrals where you have the cattle, you have the milk parlor, and then you have these sort of lagoons, which are going to be where all of the milk gets sent to slurry and then it gets separated into solid waste. And so here the goal is, we want to understand, using these flights, what are the emissions from this area, right? And let me tell you a little bit about the conventional way of estimating emissions. The way we estimate emissions in California, or the state of California, is that they use what's called a bottom-up method. So they basically assign an emission factor to a cow. So depending on the size of the cow, the age of the cow, they assign an emission. So that requires having an accurate, an accurate emission factor, an accurate assignment of the emission factor, and then actually knowing accurately how many cattle are in there, right? And if you don't know that, it's not going to happen. And this is actually why we have so much. So the idea here is to fly downwind, collect wind, collect these vertical concentrations, profiles of concentrations, and estimate what the emissions are. And so just to give you a peek of how this works, so this is the drone ascending. So on the first panel, you see wind speed versus height. The second panel, you see wind direction. And then you see here the difference between the colors. So the blue is what we're measuring ascending, and the red is what we're measuring while we're descending. So what do we see when we look at wind speed? So the wind speeds were actually highly variable, right? So they're changing a lot as we're going up and down. The wind direction is actually quite constant up to the top of the column. But then there's very interesting things happens, or it's not interesting, it's interesting that happened while we're flying, but the wind begins to shift. So essentially flying at a single location, we get a chance to look at the downwind and upwind of the air that's going over the dairy farm. So here, this is actually what you see. So we're essentially flying to the food. Yeah, it's a meter. It's 120 meters. Yeah. And one of the things to notice is, and this is sort of, we'll go back to the point of why the profession I have been talking about distributed system, right? So in this case, we did this flight in the morning, and we caught the boom, below 50 meters, right? What happens when you fly in the afternoon? This will make this a question. What do you think is going to happen? Is the boom going to be higher? Is it going to be lower? Any idea? What's your intuition? I'll show you. So these are some flights that were actually collected in the afternoon. Here, same side. Very interesting thing. So the winds seem to be more stable. They're both the wind speed and the wind direction. So these are flights actually on different dates, but they're around at the same time. So look at the plumes, right? So on one day, actually, we see lower concentration near the base, and and we see actually that the plume is off. That means the plume is quite high. So if you were to be here near the surface and you were to take the measurement of the methane, you would actually be outside the plume. If you're driving your quantification based on the surface measurement, you will get a lot of error in your. This is why it's so valuable in sort of aero robotics can provide a lot of value. And here in this other one, you sort of kind of see the plume is now again sort of kind of closer to the ground, but still there's beginning. Here I should point out from the local background is 2 ppm. So anything that we see about 2 ppm, that's actually an enhancement. Any questions? So these were here. Yeah. That's an important question. I think, especially, we want to be as close as possible to measure higher concentration. But there's a challenge here. The challenge is that the people that own the facility sometimes don't want it to come up. So it becomes a challenge of how close can we get, right? So we have some people that are very cooperative, and maybe some people that are not so excited about it. So it depends on one of the things that we've been exploring. So looking at this, within this dairy farm, there are different emission sources, and they're all of different intensity. So one of the things that we've been exploring right now is this idea of can we disentangle emissions based on the isotope signature of the gas that was measured. And for this type of work, the stronger the signal, the better that we can do this disentanglement. So the further we are apart, the more you use the concentration. Right? So ideally we want to be closer. Yeah. Yeah, that's a good question. So here, what we're doing is the tube that we use is intentionally thin. It's low diameter, or it's a small diameter. And the idea is that we want to slow the natural diffusion that happens. So we're not doing anything to separate the gas. What we're doing is we collect this measurement, and as fast as we can, we collect it, we connect it to the gas and oil. Because if you were to let that gas, that air sample for an hour in that export, it's going to stabilize. And you no longer are able to retrieve sort of enhancement. This method, it has its pros in the sense that it's very low cost, but it has its cons that there are these like concerns, right? Otherwise, the sample begins to use whatever you get, it's not natural in the atmosphere. We also did some comparisons between the drone and the ground-based observation. So the blue here is the tower that you see here at the bottom, and then the red is the flight from the drone. And you can see, at the start of the flight, this is what we're assuming at the beginning, the winds are matching quite well. As we get to the top, there's a larger error, and that makes sense because the wind is going to be higher at 120, right? But as we descend back, again, we get a good agreement. So this gives us some confidence that the drone is actually doing a good job giving us reliable information both for wind speed and wind direction. And sort of the other point that I want to reiterate is we did the same thing. So here the blue is the ground observation of methane, and the red is the drone-based observation. So what do we see is at the beginning and at the end, there's a very good match, right? But while the aircraft is ascending, there's a big enhancement. And so again, if you're just making that surface measurement, you're not going to capture where the value of these systems. Now, Measurements alone, I mean, there are of a lot of value, but for quantifying, we need some way of relaying going from our measurement to an emission rate. And so this is where I've sort of been working with it. This is the work from Professor Pula Venkatram, who's a dispersion modeler. But the idea is we collect these meteorological parameters in these concentration measurements, and then we feed them into a dispersion model, and we can essentially go from measurements that we collect to an emission estimate that's coming from our source. Right? That's the key, right? Is basically figuring out what are the best ways in which we can collect this data and assimilate it to dispersion models so we can get an emission estimate. And so this is just one framework. We're still studying experimentation, so I'll show you a little bit what we were able to do using with this framework. It's called a numerical dispersion model. So we were essentially able to assimilate the data, and we were able to generate a footprint map, which actually coincides very farm is. So in a sense, if you didn't know the farm was there, this is a good tool to basically use your weather information and your concentration information to detect where are the emissions coming from. In addition to that, we did some experiments to validate sort of the goodness of them. So it's a little bit slow. It's going to be so basically these bags. We should think of them as a receptor. So they're collecting an air sample for 30 minutes downwind of a lighting source. So we're essentially generating a source and we're releasing it for half an hour. And then we're collecting the concentration measurements downwind. We have a concentration measurement upwind. And we're also looking at the meteorological parameters. Combining these two, we're able to compare, what the model predicted, or the model predictions are at each receptor with what we actually measure. So this is our line source on the left with vector, and we have A, and that those are the receptor locations. One corresponds to the lowest height, and then 4 corresponds to the highest height. So at the utmost rock, receptors only have 2 heights. And the other ones we had 4 heights. But across all the receptors, you can see that there's a really good match between the blue and the red. So that's essentially doing quite well predicting estimates. So when we look at the correlation, it's actually quite good. And so then when we do an analysis of what the emissions were from that dairy farm, we obtain. So these are the emission estimates. These are bottom-up method that I told you, so it's about 171 kilograms per hour. This is the result that we get from the dispersion model, and this is what we get from the and so we see that the uncertainty is much lower, and there's some overlap. Right? So, this was like the first of our study, but for us it was clear that aerial robotic systems all we can profile when they're in competition reliably. You have to understand what the are and what the dynamics are. And when the key thing here is that with this technology, we can actually estimate emissions by facility. This is very critical because sometimes you can have to be very confident. But you're using the blue satellites, so this is really great for looking at emissions at a facility scale. Now more recently, after this was in July, we're looking at facility context. And particularly we're looking at the impacts that are coming from lagoons or anaerobic digesters that get placed over lagoons. And so why do we care about this? Is because what I told you that about 50% okay. 50% of the emissions are coming from dairy farms. About 50% of those emissions are actually coming from humans. So what the state has been doing is that they've been implementing these digesters to capture the methane, but there hasn't been any real, there haven't been any studies in the real world environment that are actually capturing or not. So part of the goal for this summer was to develop ways for quantifying methane from these facilities. We're just showing you a map so you can see it's actually quite easy. And there's been only 3 measurements. So I want to get to try and understand are these they enough for us to drive regulation. So we've been doing experiments where we now instead of using an air pole, we're actually using a bag to collect an air sample. So essentially in the bag, we have a temperature pressure level humidity sensor as well. Okay, so we take off and then we collect an air sample. We bring it down and analyze it. So this is just very quickly some data. Across all the flights, we're able to see we have the altitude, we have methane, right? So you see that near the surface, there are higher concentrations, and then as you go up, these concentrations go down. And that's essentially what we're referring to. Here looking specifically at data collected on the 18th, you can see we conducted our first profile, and then the second. You can notice that this thing changed. And the difference in this temperature, the reason why we think these profiles are slightly different, in the afternoon, we know that so there's, so the drones, not only can they get us concentration, but they get us relative humidity, all these things that under help dynamics, so we can better quantify emissions. And I guess I'll just skip a little bit and I can talk about this, but sort of kind of the driving point that I want you to leave with this. One is that these systems are low cost and reliable from both meteorology and composition observations. These observations are critical for quantifying methane, and therefore these systems play an important role, in my opinion, for helping us reduce overall emissions from methane. And just to get you excited for some of the conversations that Dr. Prakash and I and others have been having, again, all the work that I've shown you has been wonderful. Now we've been thinking about what we would do with the power of distributed. So what if we had what if it can more measurable? And what if they can relay information, the observations that are collected from other systems, say monitors that are out the ground, and also with data that's collected. I don't know what I'm saying, so that I'll just sort of open it up to questions. We're here for a little bit longer, so I'm hoping this is the beginning of our yes. Yeah, so the reason why we're using hexacopters is hexacopters tend to have a higher lift capacity. And so this is why we're using hexacopters. So we've actually found out that the methods that we developed for quad rotors very much the same thing. And there are some differences. The first seminar that I talked about the push and pull configurations, and we did find out that that did make an impact in the safety, but in terms of going from a fuller quadcopter to a fuller, having notice a major. Of course, one of the things that I want to do is start studying what is the sensibility of the wind sensing algorithm to inertia, because the data is going to respond much slower to a wind gust than a smaller. So I think that's important. The other thing is, I'll just get to it quickly. Sort of, I've come up with these challenges that I thought, challenges that you all, your company saw or was working on top of. Yeah, one of them is sort of understanding, the aerodynamic and control performance estimating of different aircraft, right? I started working with hexacopters. But I don't know how to work with this one aircraft. But now we see a lot of variation in between, right? And so they're there because they have obvious benefits. So what we want to do is how can we exploit reliable and reliable? That's actually a question. But I haven't seen the data. Thank you for the question. Any other questions? Yeah, I mean, I'm going in the wrong direction. Yeah, so when I look at something like this, it's obvious. When you look at the footprint of that move, it's this is a great scenario where you have to have multiple rotors combined with it. I think the fixing have longer endurance, so they can fight longer. And we sort of talked about, when we think about estimating, even if we're estimating missions, we need better transport models. In order for us to have better transport models, we need more data. In order for us to have more data, we have better drone systems. Right? So that's kind of how I see the connection, right? But we're in a scenario like this, I can see a fixed wing aircraft being a great solution for going back and forth to protect the edges of the road. And the drones, the multi-rotor drones can actually be more station keeping. See how concentrations are changing at a single point over some time, over 5 or 10 minutes. Because that's sort of kind of like the data that the dispersion model is. So I think we can have a combination of all. Yeah, so the question is, does the speed of the airplane have an impact on the quality of the measurement? Yeah, so we need to do more to validate that. For sure, what we need to make sure is that the speed of the airplane is lower than the response of the right? So that's a big challenge. So if you have a sensor that's responding every 5 seconds and you're going super fast, you're not going to be able to capture those changes, those ranges very well. So it's a combination of sort of the sensor and the aircraft in my opinion. But yeah. So sort of develop something that has like a longer wingspan that can sort of fly at a lower speed, but for a longer period of time. That would be great to sort of capture how some of these fluids are changing. Because as I showed you, and sorry I'm going back and forth so much, but look at the plumes in these 3 different scenarios. They're very different. And if you were to ask me what's the difference, what's going on between the left and the right, there's very low wind on the left. So the plume is just sort of, yes, it's but it's sort of staying there, right? It's floating away. On the very right side, you have a storm that's causing the emission. Basically, comes back from satellite. Yeah. And so there are pictures of the plume, right? So in this case, yeah, I mean, it'd be great for us to keep persistent measurements so that we can understand how the plume is changing shape under different atmospheric conditions. So this is, I think there's a lot of value. Yeah. Yeah, so the question is, why is the variation so high? And that's the question that every scientist wants answered, right? And that's the limitation. I think this is one of my conjectures, and I haven't talked to them enough to understand how they're doing it, how they're actually estimating it. But I think they're modeling the wind field. So they're, if you're modeling the wind field, the Central Valley is a challenging area to. So this is where, I think it's great to use a model, but if you can run that model in actual operation, that would lower the. That's exactly the point. That's exactly what's motivating these other measurements. Use drones to let other information. We can really see if these technologies are actually working the way they should. So that we can make decisions quickly. Otherwise, we're in the what is this? Yeah, that's a great question. So, I should have put something there. But I couldn't tell you in meters, but I mean, I want to say that it's about 30, I mean, you can see this here. This is the two labels, just sort of for context. So when you're there, these facilities are actually quite large. Yeah. Oh, yeah. Thank you.